presentation in Unit 6. This is called Sharing is Caring. And as you see here, it says, hey, can you remember the formula for nitric oxide? And the answer is no, and that means nitrogen and oxygen. So you should be able to get these kind of jokes as you go through. One of the things you're going to learn how to do is you're going to learn how to name covalent compounds, just like you learned how to name ionic compounds in the last unit. It says sharing is sometimes more demanding than giving, and if you did the engage activity, you know exactly what I'm talking about. The learning goals are that you understand the nature of a covalent bond, and that you distinguish between a polar and a nonpolar bond. What's the difference between the two? And then finally, you'll be able to write the chemical formula or the name for covalent compounds. So we already know that atoms can combine to form compounds. In the last unit, we talked about things like sodium chloride, and that was an ionic compound. Now we know that the reason why these things interact is because there's an interaction of electrons. In fact, there's a transfer of electrons from sodium to chlorine. Now we know that there's an interaction of electrons to form a bond, but we're going to talk about a different kind of bond. We're actually going to talk about where you share electrons as opposed to transfer one from one to the other. Now, what we learned in the lab, we learned that covalent compounds share electrons. We learned that covalent compounds do not conduct electricity and that they have much lower melting and boiling points than ionic compounds. We also learned that they tend to be mostly liquids and gases at room temperature, and that when you do have a solid or a liquid, it has a very different structure than you have when you have an ionic crystal. So, reviewing the octet rule, we know that atoms are most stable when they have a filled orbital shell. And for elements less than 36, what that means is that they want to have 8 valence electrons. Okay, now we do have some exceptions. There's hydrogen and helium. As we'll talk about a little bit later, you can actually have things where like phosphorus or sulfur can be exceptions as well. But for now, the octet rule is everything wants 8 valence electrons in its outermost shell, 8 valence electrons. So, one of the ways that this can happen is you can actually share electrons between things. Carbon generally has 4 electrons. If it's got 4 electrons, what it needs to do is it needs to share these electrons or give them away or take some sort of electrons. Well, hydrogen has 1 electron as well. If they share them and they put them together, carbon thinks it gets these 2, hydrogen thinks it gets these 2, so they are both satisfied as far as carbon gets an electron, hydrogen gets an electron, and because of that, they have increased stability. So each atom thinks that it has the shared electrons. And that's what you see right here. This is the molecule of methane, and it's got 2 electrons that are shared right there, 2 electrons that are shared right there. And if you see, the carbon thinks it has 8 valence electrons. The hydrogen thinks it has 2 valence electrons, when in reality, they're sharing them all. So covalent bonds are, whenever ionic bonds form, electrons are removed or added. A covalent bond is when the electrons are shared between 2 things. So it's not a tug of war between the electrons, they're equally distributed between them. So, how do you determine if something is a covalent bond? Well, if it's a covalent bond, what you need to do is you need to look at the electronegativity. Remember, the electronegativity we talked way back when we talked about periodic trends is the measure of an atom's ability to take an electron from a shared pair. And it depends on the valence outer electron's distance to the nucleus, so the distance, and it depends on the number of protons, or really the effective nuclear charge. And it also depends a little bit on the stability of the ion, but remember, it depends on Coulomb's law and effective nuclear charge. So because of that, you can say that you can predict the electronegativity, or you can remember the trend. So this is the trend. Electronegativity decreases as you move down the periodic table. So francium over here is the least electronegative, and fluorine over here is the most electronegative. Now we exclude the noble gases because they don't really want any electrons. A covalent bond always forms between 2 nonmetals. So when you were to look at the periodic table, everything, so there's a little stair step right here. Everything to the right of that staircase forms covalent bonds with one another. Because of the nature of covalent bonds, they tend to be gases or liquids at room temperature. So they tend to be things like water or oxygen gas. they have extremely low melting points. It's very, very, very hard for you to see a solid oxygen. It's actually very difficult for you to see solid water. And you say, well, I see ice all the time. Yes, but compared to something like salt or compared to some other sort of ionic compound, it's much, much more difficult to get solid water than it is to get solid salt. They also have very, very low boiling points, which is evidenced by oxygen being a gas at room temperature. So the first question we have, it says, draw what happens to the electrons in a covalent bond between chlorine molecules. So if you were to look at this, you have chlorine, in which you have an electron right here that's not paired. You have an electron right here that's not paired. What happens is this electron will actually move over here, or the molecules will orient themselves so they can actually take these electrons and they can share them. These electrons right here would replace over here and go to the other side because they're a complete thing. So instead of writing the dots, which we could write the dots as shared electrons between the two. We tend to write it instead as a line. The line right here represents a shared pair of electrons. So we would generally draw it as this. You got to make sure you put all the other electrons there because those other electrons are there and they're unbonded electrons. So covalent compounds have a much lower melting point than ionic compounds. Use Coulomb's law to explain why. So whenever you have a sodium chloride, you have a positive charge and you have a negative charge. And then you have another sodium chloride where it's a sodium and a chloride. And there's an attraction here. We call this attraction an intermolecular force. And you may not talk a lot about intermolecular forces this year, but in subsequent chemistry classes, you'll talk about them quite a bit. But because there's a positive charge and a negative charge, it's really hard to separate molecules of salt from one another. Now, the whole process of melting is where you kind of break this connection and allow these particles to move relative to one another. They can move all around. That's what being a liquid is. And being a gas is actually being able to move against gravity independent of anything else. So because you have a positive and a negative charge, it's really, really hard to do that in an ionic compound. But whenever you have a covalent compound, you have either no positive or negative charge, or in the case of water, you have what's called a partial negative charge. Think of it as a fraction. So where this is a full positive charge, a partial negative charge or partial positive charge can be like a negative 1/20th and positive 1/20th. So those partial charges aren't nearly as strong as you have when you have a full ionic attraction. You can share electrons equally between atoms. When you share electrons equally between atoms, it tends to be the same element. So you have something like nitrogen and nitrogen. Nitrogen and nitrogen will share electrons equally between them. Now the reason why they'll share electrons equally, and we call this a nonpolar covalent bond, is because the atoms have the same electronegativity value. Remember, electronegativity is how much it wants an electron. So if I have a chlorine that wants an electron and a chlorine that wants an electron in an equal amount, it's like a tug of war. Okay, those electrons don't go anywhere because they're pulled equally. Now, it doesn't have to be exactly equal to be considered a nonpolar bond. In fact, if they have an electronegativity difference of less than 0.4, it's considered to be a nonpolar bond. Like when you have carbon and hydrogen, that's considered to be a nonpolar bond, even though there is a slight difference between the two. Now, the only ones that are truly nonpolar are the ones where you have the same element, like a nitrogen and a nitrogen, or a carbon and a carbon, or a chlorine and a chlorine. Those are the only ones in which you have an electronegativity of 0 whenever you subtract them. And we call that it has a dipole of 0. Sharing unequally. So not all electrons are equally shared between atoms, and the shared electron tends to gravitate towards one atom or the other. And that brings the famous quote, all animals are equal, but some animals are more equal than others. And you can just replace animals with atoms, and you have the same basic idea. So all atoms are going to share, but some are going to share more than the others. That's what you have a polar covalent bond. A polar covalent bond is one in which you're sharing electrons, but you're not sharing them equally. So what you see is you see water. water has oxygen in it that is highly electronegative. If you were to look at its electronegativity value, it's actually the second most electronegative element on the periodic table. And then you see hydrogen, which has a pretty low electronegativity value. So when you subtract them, you actually get a pretty decent number. You get a number that's between 2 and 0.4. So because of that, you actually get the electrons kind of gravitate towards the oxygen. Well, when they gravitate towards the oxygen, it actually makes the oxygen have what's called a partial negative charge. And you have the partial positive charge on the hydrogens, because even though it has these two electrons, it doesn't really have them. It's actually closer to oxygen. So because of that, you have what's called a polar covalent bond. Now, remember what we talked about before, you have a partial positive charge and you have a partial negative charge. So these polar covalent bonds are going to be a little bit different in their properties than the non-polar covalent bonds. So we have an example. This is the carbon-hydrogen bond. It's the basis for life as we know it. And this is describe the type of bond formed between carbon and hydrogen using your periodic table of electronegativities. So if you were to kind of scroll in right here, you would see that hydrogen has a value of 2.1 and carbon has a value of 2.5. So we can kind of scroll out from there, and we can say that the change in electronegativity values would be 2.5 minus 2.1, which actually gives us a value of 0.4. Now, since we have a value of 0.4, that actually makes it a non-polar bond. Now, it's really hard to describe things as polar and non-polar, because really what you have is you have a continuum. You have things that have an electronegativity difference of 0, and that's whenever you have the same element. Those are the things that are truly, truly non-polar. And then you have kind of a gray area right here, and then we have this cutoff, and we say this cutoff is where things are polar. And then it goes, and then we say we have this cutoff where it's now ionic. Well, it's not really cutoffs, it's more of a continuum between the two. So if you were to choose an element, let's say right here, and an element, let's change the color, right here. Well, both of these would be considered to be polar at some point, because you haven't, or excuse me, non-polar. They would both be non-polar because I haven't gotten to the polar part yet. But if you had to describe them, you would say this blue one is more polar than the red one, even though it's not polar. So it gets to be kind of confusing when you use the terms polar and non-polar. There are no real absolutes. The general thought is, hey, if it's 0.4 or less, it's non-polar. But you have to think of it as a continuum, not an absolute. Okay, the next question says, using Coulomb's law, compare the properties listed below for polar covalent compounds versus non-polar covalent compounds. So, at boiling point. So the first thing you were to look at, let's give an example. So I have HOH. Now we said you're going to have a partial negative and a partial positive here, and a partial positive. So because I have those partial positives and partial negatives, those right there are going to have some attraction to the next water molecule. So my next water molecule is going to be a partial positive, and there's going to be some sort of attraction right there. In fact, if you remember anything from biology, that's actually called a hydrogen bond. And it's what happens whenever you have DNA molecules connect together. So this hydrogen bond has some sort of attraction to it. Now, whenever you have something that's completely non-polar, like let's make it easy, let's just say chlorine and chlorine, there is no net pull one way or the other. So because of that, there is no positive or negative. Well, if there's no positive or negative, there's no attraction. Well, if there's no attraction, then these things have very, very low boiling points. And these things are in the middle. Okay, they're not high, because high would be ionic. This thing right here, extremely low conductivities. No electricity will flow through this thing at all. This thing, it's pretty low, but it's low middle. You are going to have some electricity that's conducted, just not very much. And finally, melting point is going to follow the same trend. This thing is going to have an extremely low melting point, and this thing is going to be in the middle of the road. And it all has to do with these things that we call intermolecular forces. The molecule CH4 forms a tetrahedral shape as shown. It says describe whether the molecule as a whole is polar or non-polar using your table of electronegativities. This is really interesting because the individual bonds here are non-polar, but they have some sort of polarity to them, 0.4. So if you have all the hydrogens kind of on one side, those 0.4s can kind of add up. But the reason why It's interesting is this molecule, based on the shape that it takes, you have a pull here, you have a pull here, and you have a pull here. Well, what they're doing is they're canceling each other out in every direction except for the down direction. So you have a net pull downwards. But you have a molecule on top that has that net pull upwards. And these two things would cancel each other out. So the shape of the molecule says that you have no polarity whatsoever. In fact, I would say that this has what's called a dipole. A dipole refers to the molecule as a whole of zero, because there is no polarity for the molecule at all. Finally, we need to come to naming covalent compounds. Now, naming covalent compounds is much, much, much easier than naming ionic compounds. All you have to do is name the element first, attach a prefix if necessary, name the second element, switch it to "-ide", and then put a prefix if necessary. Now the prefixes are mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. And they go on from there. There's a whole list to 1,000 or something like that. But these are the only ones you need to know, the first 10. Now there are rules, and it says you have to identify the first element. It moves left to right across the periodic table. So you would always name nitrogen before you would name oxygen. You would always name oxygen before you would name fluorine. Now it also says that hydrogen is in between nitrogen and oxygen. So hydrogen actually goes right here. That's kind of strange. People kind of mess that one up, but that's where it goes. So now you would determine if a prefix is necessary. The first element, okay, so for example, let's say you have NO. This right here only has one N. So a lot of people will put mono right away. Mono is not put on the first element unless mono is never put on the first element. If it's N2O, you do have to put di. So the mono is implied on the first element unless it says something specifically otherwise. So the best way to kind of get into these is to practice them. So it says write the chemical formula for dinitrogen pentoxide. So remember, di means 2, nitrogen means N, penta means 5, oxide means O. So when I write this out, it would be N2O5. Carbon tetrachloride. Carbon, there's no prefix, which lets me know there's one carbon. Tetra means 4, chloride means Cl. So I'd say CCl4, carbon tetrachloride. Now you're going to be expected to do that in the reverse. You're supposed to be able to name the compound based on what's here. So if you look at this, I look at it from, first I've got dihydrogen. And you say, oh, that's water. Yes, it's dihydrogen because there are two hydrogens, and now I only have one oxygen. Now I have to put mono in the second part of it no matter what. So it's dihydrogen monoxide. And remember, you always end with an "-ide". So I look at this one. I've got carbon, but there's one of them, and it's the first one listed. So remember, you never put a prefix mono for monocarbon, the first one. But you always put it for the second one. So I have carbon, and now I have to say monoxide. Ends with "-ide". The last one, we have one phosphorus. So I'd say phosphorus. And then I have 5 Cl's, so that would be penta. And then I would say chlor, and then I have to end it with an "-ide". The last thing we need to talk about real briefly is metallic bonding. Now, metallic bonding occurs whenever you have things that are like transition metals, you know, that big block in the middle, that bond with one another. And so it's a special type of electron sharing. So because of what we have, what is called the delocalized nature of the d orbital shell, these electrons can actually kind of coexist between multiple molecules. And it's kind of referred to as electron communism. This right here doesn't belong to this, it doesn't belong to this, it doesn't belong to this. It belongs to the whole group of atoms. And so because of that, we call this thing a special type of bond called metallic bonding. And so the most common term that you see is this: the metal atoms have become surrounded by a sea of electrons. So this atom exists, and then it's got a sea of electrons that it's kind of in. This property is actually what makes these things very, very good conductors, because there's a sea of electrons that surround it. So when I put electrons in, it just makes the electrons kind of bump through. So the delocalized electrons allow for the free movement of electrons, and you can see that here. The electron comes in, it comes out, it comes in, it comes out, and it allows this free electron to kind of move all the way through the atom. It also allows for the transfer of energy via thermal conductivity. So if you think about this as, hey, there's a lot of energy here, it made this electron be really excited, that knocked it to here, that made it be really excited, that made it here, that made it be really excited. That's the transfer of thermal energy as well. But it also explains why metal ions can slide past each other. So the malleability and ductility. So because of the way these things have electrons kind of just randomly through here, the fact that I move this atom over here and I move this atom over here, there's really no difference in terms of the electrons. So use the description of metallic bonding to explain why solid metallic bonds can change shape easier than solid ionic compounds. And the reason is this molecule can just move relative to this one because the electrons that are in there, there's no charge that's holding it in place. There's no strong force, so no opposites attract, keeping it where it needs to be.